Hi everyone, thank you for joining. I'm Mattia. And today I'm going to present you a visual metaphor that we developed in our lab with Professor Michele Lanza and Dr. Marco Aurelianti to visualize object-oriented software systems. So the main reason, the driving reason behind this new visualization is that source code is hard to be understood, especially at scale. The first reason why is that IDE shows source code, visualize source code as text, one fragment at a time, making it hard to visualize the whole structure of the software system, both at small scale if the single file is huge, or large scale if the software system is very large. The process of mentally piecing together the role of a class or its behavior is cognitively demanding, and it's also slow and error prone. Especially in a large software system, this doesn't scale because maybe relationships span many files or many components, and there is no single view that can show in an IDE the whole picture of the software system. And this is an issue because poor comprehension of a software system can lead to fragile changes or regressions or architectural erosion. Software visualization hides broken comprehension by depicting the entities of a software system, but existing approaches tend to the extremes that are detail or scalability. For instance, UML class diagram have a much detail. It's a standard notation, so it's very good. But with large software system, tend to visual clutter or hide the whole context, the whole picture of the software system. On the other hand, visualizations such as volumetric views provide system-wide overviews, encode multiple metrics, but they only provide the minimal details and lose the semantic role of a class. So it's very hard to reverse engineer the semantic role of a class. This is why we propose class contour, which is a novel visualization that uses the well-known city metaphor for the visualization. It depicts each class as a two-dimensional architectural element. And with this visualization, we try to balance detail and scalability. So let me explain you how to read a class contour. First of all, we visualize each class as a building, and we split each building into two sides, which are the instance side and the class side of the class. On the width of each side, we map the sides of the class in terms of a number of lines of code. Then we map the superclasses on the steps that lead up to the building, and the constructors of the class on the decorations of the facade. Then we map the attributes on the doors of the building, and the windows represent the methods of the class. Finally, we group the methods according to their visibility. So the ones that are most visible from the street are the lower ones, and the ones that are the more hidden from the street are the private ones. As I said, each door represents an attribute, and that's why we want to visualize the information that are contextual to the attributes near the doors. So the getter and the setter of the attributes are visualized as the door panes on the door. And we have 4 different combinations, which are class with no accessors, with both of them with only the getter or the setters. And as I said, the windows represent the methods of the class. So we map the size of the method in terms of number of lines of code on the width of the window, then the parameters on the blind elements of the window, and then the blocks of comment that document the code, which are nice to have on the flower pots on the windowsill. And the size of each block of comment is the width of the flower pot. Each window can be lit if the method returns a variable value, and unlit if it returns a constant value. And we also can visualize that code. So if the method is not invoked, we visualize it as a barred window. 3 reflections on class contours. First of all, this is not the only mapping. For instance, if we want to visualize a software system, which is a software library in which many methods doesn't receive invocation because they're meant to be invoked by the system that uses the library, of course, I'm not going to visualize that code as method not being invoked. And another thing is that we don't want to overload the visualization with too much information. So, for instance, this is why we don't use the size of the door, so all the doors looks the same size, and the height of the windows. The second reflection is that class contours can be used on a small scale to visualize, to reverse engineer, to understand the semantic role of a class. So these enable role recognition without inspecting the source code. And the last reflection is that class contours can also work in the large picture of the whole software system. So even here in this small figure, you can see that there are some classes that are huge and some that are very small, some that have like a very narrow shape and so on. Let me dive deeper into how to use class contour on a small scale. So as I said, identifying the role of a class is hard just by reading the source code or by looking at those kind of visualizations, such as the class diagram, because you have to go all the members one by one and try to figure out what is the goal of each method or attributes. And in this visualization, for instance, all the methods are visualized the same, so there is no distinction between the getters and setters or the methods that implement the logic of the class. This is an example of how the class contour of a data holder looks like. So here, the class has there's no methods, so no windows, and many attributes. So here is clear that the semantic role of the class is holding data and providing access to those data. This is another example of the class contour of a utility class. So here, the classes have an empty instance side. So the left side is empty. And there are a lot of static methods which are exposed through the static interface of the class. And one may argue that it is easy for such a class to understand the role by looking at the UML diagram because it's like only static methods, and going one by one is easy. But when the class is larger, it's harder to go one by one and check if each method is underlined. Moreover, the visualization also conveys more information, such as if the attributes are variables or if they are constants, which are, in the case of Java, for instance, static final of immutable type. This is another interesting case. Here, we have a building which has many small windows, which are many small public methods, and only one single attribute, one door. While developing this metaphor, we, of course, visualized a lot of systems, a lot of classes, then inspected the source code to figure out if the visualization made sense with respect to the visualization. And one thing that we noticed is that in this case, this particular pattern always corresponded to a wrapper class, which is a class whose semantic role is those of receiving invocation and forwarding the invocation to the wrapped instance. As I said before, class contours can also be used to identify anomalies, not only patterns. So here, one of the most straightforward one is the one of large methods with respect to the other methods in the same class. Or for instance, this is a nicer one. So here, this class has only 8 public methods, which are very small, and are instance side, but it doesn't define any instance side attributes. Otherwise, it should have a door, at least one door. And it doesn't inherit any attribute from the superclasses because it doesn't have superclasses. Otherwise, it would have steps leading to the building. So what's the point of having instance-side methods if there is no state that can be used by the instance-side methods? In some cases, it makes sense. For instance, if a class implements the runnable interface in Java, it has to, of course, implement the methods defined by this interface. But this is like how. This is specific to some languages. It's not universal to all the object-oriented languages. Class contours can also be used on a large scale to convey information in the larger, broader picture of the whole software system. So here, for instance, I visualize the whole code base of Antler. Each package is visualized. If it has no classes, it's just a dot. And if it has classes, we can visualize the skyline of the package. And also here at a large scale, the containment between packages is visualized as connecting lines between the packages. Also here on a large scale, it is possible to identify, for instance, very large classes, which are large chunks of implementation logic. Or for instance, this is a data class because it has a component of data class because it has some methods, but it also has a very, very large number of attributes. It is also possible to identify patterns across multiple classes. So here, all the classes are very, very similar. They all have one constant and some methods. And it is also possible to identify patterns across multiple packages inside the same software system. They all have two classes which look more or less the same. So where do we go from here? One direction that we already started exploring is analyzing those visualization patterns and building detection rules that we use to identify class archetypes at scale. Class archetypes identify the semantic role of a class and do not require visual inspection like the class contours, but they are born from the visual patterns of class contours. Another extension is bringing class contours to 3D, because as you may know, my master thesis was about interaction in virtual reality. So one of our goals is bringing class contours to extended reality, specifically augmented reality. And another thing is that we want to develop one specific building for each one of the archetypes, so that it's easier to distinguish between among the different semantic roles, and it will bring to a richer visualization and easier to understand the role of the classes into the software system. So with this, my seminar is concluded. Thank you.